Hi, my name is Matthew Timms, and in this video I will be presenting my ECSE final year project, which looks to investigate the issue of diversity loss in generative adversarial networks. Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. It allows for the rapid parameterization of mathematical models that help describe, classify, and generate data. The optimization of networks' objective functions, a measure of neural networks' performance, allows for parameters of the network to be updated to move the output closer to the desired target output. However, some mathematical models are too complex to define objective functions to solve. For example, how do you define a function that will teach a machine to draw images of human faces? Generative adversarial networks, or GANs, offer a solution by simplifying the objective function. GANs employ two separate neural networks in competition against each other, a discriminator and a generator. A common analogy for this network is to describe the discriminator as an art expert who is learning to identify real paintings from forgeries. The generator acts as an art forger who is learning to fool the art expert with forgeries. The objective function for the generator is to maximally confuse the discriminator, and the discriminator aims to maximize correct predictions. Through this adversarial process, a GAN can learn to generate new data that fits the data distribution of its training set. Applications for these types of networks include image and video modifications, such as style transfers, super resolution, and superimposition. However, stability during GAN training is notoriously difficult. This arises from the issue of network diversity loss, referring to the ability of the generator to sufficiently represent the multimodal distribution of the network's training set. After sufficient training, an ideal generator should be able to represent all modes rather than collapse to represent a single or few modes. This behavior is undesirable in generative models, and furthermore promotes training failure. It is easy for humans to detect mode collapse by observing the image similarities of generated samples. This project investigates various GAN implementations, the issue of diversity in GANs, and looks to incorporate additional information to the discriminator such that it can make smarter decisions to improve generator diversity and network training stability. The software written for this project was completed in Python using the machine learning framework PyTorch. Keras and TensorFlow frameworks were developed with initially. However, PyTorch offered increased performance and significantly easier means of network debugging, which proved vital to meeting the project's objectives. A deep convolutional generative adversarial network, or DC-GAN, was adopted to base the investigation upon. This network varies from the original vanilla GAN model by relying on convolution layers, which have been shown to perform better with networks handling visual data. Convolutional layers perform strided matrix operations using a multidimensional kernel of trainable weights against the input tensor, a general term for matrices of high dimensions. These convolutional layers act to spatially upsample and downsample data. The DC-GAN also incorporates batch normalization for both the discriminator and generator to reduce internal covariate shift. This refers to the changes in the distribution of each layer's input that occurs during training as the previous layer's parameters change, which commonly requires slower training to avoid learning problems and encourage network convergence. Batch normalization attempts to keep the input distributions fairly constant during training, which promotes higher learning rates. This is achieved by normalizing the feature vector with other feature vectors in the same sample batch. It is performed after convolutional layer operations and prior to layer activation. Since normalization occurs across a batch of samples, it is then required that the discriminator receives input batches that contain exclusively all training data samples or all generated samples, instead of a mixture of both. Leaky ReLUs are also chosen as the activation functions for the discriminator, as it was shown to improve network stability. Leaky ReLUs have been suggested to minimize a learning issue referred to as dying ReLU. This is when the ReLU neurons repeatedly output 0 for any input. The function gradients subsequently fall to 0, and ultimately, no error signals are passed to earlier layers for weight updating. In severe cases, large sections of a neural network become frozen by dead ReLUs. Logging the network's performance during training was performed with a PyTorch implementation of TensorFlow's visualization tool TensorBoard. After each epoch of training, which is when the entire dataset has been passed through the network, a grid of generator-sampled images would be saved to visualize the progressive learning of the generator. A script was then written to turn these images into a .gif image file. Network performance metrics, such as loss, were logged and visualized using TensorBoard as well. This allowed for easy observation of GAN performance over training periods and helped to identify network behavior that related to training failure. Ultimately, this prompted the design and implementation of methods that would stop network training early if failure was detected. For example, if loss metrics saturated, this was a sign that the generator was producing indecipherable images of noise. The saturated values would cause the learning gradients to fall to zero and cause the network to be incapable of making significant changes to recover. As discussed earlier, GAN evaluation methods commonly involve visual inspection of generated samples to evaluate their quality, as well as signs of overfitting or mode collapse. To make this process easier for users, software was developed to automate certain processes relating to GAN evaluation. To avoid outputting images throughout training, network parameters were saved after every epoch as checkpoint files. These files could then be reloaded for further training or to output image samples. To evaluate instances of overfitting, software scripts were written to calculate the color distance of source images to target images. For example, training set images to a larger set of generated samples. A number of closest images would be outputted along with the source image for visual inspection. Instances of overfitting would be observed if the closest images appeared identical to the source image. Color distance calculations were also employed to calculate distances within an image set. The comparison of distance histograms of image sets can show how the generated distribution varies from its training set. A histogram of smaller distances compared to its training set's results suggests that the generator has not completely fitted to the modes of the training set, a sign of diversity loss. Ultimately, these scripts act as a form of image clustering. Alternative clustering techniques could also be employed, such as k-means clustering. Since it was easy for humans to detect mode collapse through visual inspection of generated samples, it was hypothesized then that feeding additional information about other generated samples may help the discriminator to make smarter decisions and prevent the generator from collapsing. The first approach involved passing input images as pairs to the discriminator, such that the network could examine multiple images for similarities prone in mode collapse. Developing further on this image pair concept, it was suggested that the pairing of input data occur at some intermediate layer upon the feature vector outputs of convolutional layers, similar to the practice of mini-batch discrimination. To describe this process, the discriminator's architecture was separated into halves, referred to as the discriminator head and tail respectively. The output of the discriminator head is a tensor of image input feature vectors. This tensor is then reshaped such that the pairs of feature vectors would be passed to the discriminator's tail. The process of pairing images requires input batches to be exclusively comprised of only real or synthetic samples. Research investigated where feature vector concatenation should occur and found that the best results occurred after the second hidden layer of the discriminator. Similarly, the amount of paired concatenation was examined between pairing of 2, 3, or 4 input image feature vector pairs. That is to say that the batch would be divided by this pairing number, also referred to as the number of discriminator heads, and all possible pairs would be made with the feature vectors in each group. This gave rise to the colloquial name for the GAN, the multi-headed discriminator, or hydroGAN. However, this may be misleading. This GAN does not, for example, employ multiple discriminators, much like how the multi-agent diverse GAN employs multiple generators. Regardless, this project evaluated subsequent GAN performance using a two-headed model for a number of reasons. Most significant was the effect of this concatenation upon a network with a fixed number of trainable parameters. While hydroGAN increases the amount of information passed forward through the network, it does not increase the number of network parameters available for training, and this is noted as an area for further research, to vary model capacity based on the number of discriminator heads. Gaussian noise was also introduced to both the training and synthetic data before being passed to the discriminator. Adding noise to the discriminator's input is a method of regularization that reduces the influence of hidden sources of information affecting the decision of the discriminator. These hidden sources of information may not be what the discriminator is meant to learn. For example, this could be image watermark artifacts caused from JPEG compression of ground truth labels. A discriminator may learn to identify compression artifacts and collapse the decision-making process to value the presence of these artifacts alone. Alternatively, the generator may learn to generate these watermarks to fool the discriminator rather than learn to generate high-quality images. The use of label smoothing was explored, where target labels used to evaluate discriminator loss were sampled with noise. A real label, for example, would be randomly sampled from a range. This has been shown to improve generalization, however the benefits of label smoothing were imperceptible during this project's testing, and were removed until further investigation could be conducted. The multi-headed DC GAN, or hydroGAN, was successfully designed and trained. Training performance was observed to last on average for more epochs than the original DC GAN. However, image quality of generated samples is arguably poorer than samples from the DC-GAN model. This could be attributed to the larger amount of data passed forward through the network compared to the model's capacity, which has not increased. As a result, training could be considered to converge slower rather than to have improved training stability, similar to criticism presented about the Wasserstein-GAN stability performance. These generated images show crisp quality, and signs of convergence are clear in the plot of its discriminator's loss, exhibited by the loss values decreasing over time. Notably, this figure of birds shows a separately trained generator that has generated a completely new bird that looks to fit the training data's distribution. Furthermore, a test of its closest neighbors from its training set showed that the generator is not overfitting. The inclusion of Gaussian noise layers throughout the discriminator was observed to improve training stability. This table shows the average training epochs of the original DC-GAN, two-headed hydroGAN, and a two-headed hydroGAN with noise layers. This project prompts further research into providing the network with additional information, such as image statistics, to improve stability and diversity. Mini-batch discrimination is a promising method of improving the network. This technique includes adding image distance metrics about each image in the training batch to the discriminator along with the sample image. While it was not successfully implemented in this project, further research may yield better results. Methods for network improvement explored in this paper have been isolated to the discriminator. Further research should consider possible modifications that include the generator. Much like the issues of the inception and Frechet inception distance scores, evaluation methods implemented focused on generated samples and not the performance of the discriminator. Research into evaluation methods that include the discriminator should also be considered. Research into GANs over the past 4 years have brought forth many implementations that build upon Goodfellow's original paper. Further research should take time to look at these alternative networks and to evaluate their modified objective functions, architectural differences, and training processes. Generative adversarial networks represent a breakthrough in training generative models. This project investigated various GAN implementations along with the associated problems with their training. By modifying the training process with an alternative design of the DC-GAN's discriminator, train stability was shown to improve compared to the original DC-GAN. An image clustering technique was presented and used as an evaluation method to identify issues of overfitting and mode collapse. Recommendations for further research were presented that look to expand evaluation methods to consider the nature of the training dataset and each component of the network. Improved network performance is achievable through further investigating various modifications to networks' objective functions and architectural designs. Thank you.